These are examples for section 13.3, area of regular polygons. Example 1. The figure below is a regular pentagon with radii and an apothem drawn. Here's an apothem. By our definition, it's perpendicular to any one of the sides, and it starts from the center. And we have all the radii drawn. Remember, radii of a regular polygon always start at the center and go out to each vertex of the polygon. This happens to be a pentagon with 5 sides, and so n is 5. And so we're trying to find the measure of each one of these angles in the pentagon. Starting with angle 1 here. Angle 1 is a central angle because it uses both radii here and here, and it's the angle in between the two from the center. So to start off with, n equals 5, the central angle measure is equal to 360 degrees, because we're going all the way around the center, divided by the number of angles or sides, 5. So 360 divided by n. So 360 degrees divided by 5 in this case, when you divide you get 72 degrees. Therefore, the measure of angle 1 is equal to 72 degrees. 72. Then moving on to the apothem. Here's the apothem right here. The apothem is drawn in this triangle, this right triangle. I pulled it out here. So this is the apothem that came from here. This is one of the radius, or radii, right here. This is angle 2. Of course, we already found angle 1 right here, which was 72 degrees. Now, this is also a central angle here. The apothem bisects a central angle no matter where you draw it. And so, for that part, draw apothem, if you need to draw one. And that means that the measure of angle 2 is equal to the measure of the central angle, 72 degrees, right here, divided by 2, since it cuts it in half. And that gives us 36 degrees, so the measure of angle 2 is 36 degrees. So this is 36 degrees. Finally, the measure of angle 3 can be found relatively easy by using the triangle angle sum corollary. If it's a right triangle, we take the two acute angles, and the sum of them should be 90 degrees. So by triangle angle sum corollary, we have the measure of angle 3 plus 36 degrees equals 90 degrees. Subtracting 36 from both sides, the measure of angle 3 gives us 54 degrees. So the measure of angle 3 is 54 degrees. So we found all 3 angles. Example 2. What is the area of the regular decagon shown below? Decagon meaning 10 sides, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n is 10. And we're asked to find the area of a regular polygon. The formula is area equals 1/2 times the apothem's length, lowercase a, times the perimeter of the regular polygon. Recall that the perimeter of any regular polygon is ns, where n is the number of sides and s is the length of any one side. Well, we need the apothem. The apothem's given to us, or one of them is, right here, which is 12.3 inches. So the apothem is 12.3. We also need the perimeter. The perimeter can be found by taking the length of one side, which is 8 inches, so S is 8. And using P equal NS, perimeter is the number of sides, which is 10, times 8 inches. And that, of course, gives us 80 inches. So it's 80 inches all the way around this regular polygon. So we have what we need now. Come back up here and substitute it into our formula. The area is 1/2 times the apothem, which is 12.3, times the perimeter, which is 80 or 80 inches. At this point, 2 and 80 are divisible by 2. 2 goes into 2 once, 2 goes into 80 40 times. Now we have 1 times 12.3 times 40. And when we multiply those two together, we get 492 square inches. The area of this regular decagon is exactly 492 square inches. Example 3. The gazebo in the photo is built in the shape of a regular octagon. Here's the top view of it right here. Gazebo. Each side is 8 feet long. And the enclosed area is 310.2 square feet. So the area in here they give us is 310.2 square feet. They give us the area. What is the approximate length of the apothem? The apothem A, rounded to the nearest hundredth of a foot. Well, they're not asking for the area, but we're using the area of a regular polygon, octagon in this case, so n is 8. And we use the formula for the area of a polygon, A equal 1/2 AP, apothem times perimeter. So we need the apothem and we need the perimeter. We can find the perimeter relatively easy. The perimeter is ns, or n times s. So P is the number of sides, which is 8, times the length of each one of the sides, which is 8 feet. Remember, it's regular, so all the sides are 8. So 8 times 8 feet is 64 feet, and so we have our perimeter. Now we need to find the apothem. To find the apothem, let's go ahead and draw one apothem. It can be anywhere as long as it's perpendicular to one of the sides. I'm going to use the one at the bottom here. From the center, perpendicular to it. And so any apothem does several things. It bisects a central angle. So let's go ahead and draw both radii on either side of the apothem. This one and this one. And so it just caused this angle, the central angle here, has caused there to be two congruent angles there because of the apothem. It also causes these two pieces of the side to be congruent if we were to need them, 4 and 4. But they're asking us to find the apothem. So since we're looking for it, we have everything we need. We've got the area here and we've got the perimeter here. So we're looking for the apothem. So for A, it's 310.2 square feet equals 1/2 times A, the apothem, times the perimeter, which we found is 64 feet. Solving for A, 2 goes into 2 once, 2 goes into 64 32 times, and so we get 310.2 equals 32 times A. Then we divide both sides by 32, and when we do that, we get an approximate answer of about 9 69 hundredths of a foot. So rounded to the hundredth of a foot, it's 9.69 feet. This apothem right here. Example 4, zoology. A honeycomb is made up of regular hexagonal cells. The length of a side of a cell is 3 millimeters. Here's one of the cells blown up. It's 3 millimeters. Excuse me, millimeters, not centimeters. So each one of these is 3. It's regular. What is the area of the cell? Since this is a regular polygon, we are going to end up using A equal 1/2 AP. Now, when we're finding the area of a regular polygon, depending on what they give us, will depend on how involved the problem may be. So far we've only had one where they gave us the apothem. That was a relatively simple problem. We just plugged it in. Of course we did have one of the sides. Here we only have a side. We don't have any radii and we don't have the apothem itself. So when this happens, the first thing you want to do is draw two adjacent radii. And it can be anywhere. I'm going to use these bottom two, this one and this one. They're radii to each vertex. But I'm going to draw this one and this radius. And so, a measure of a central angle we're going to need right here. So the number 2, that was 1. Number 2, find central angle measure between the two radii. So the measure of that angle, of course, to find that we use 360 degrees divided by n, the number of sides or angles in the regular polygon. Here it's a hexagon, so n is 6. So we have 360 degrees divided by 6. That gives us exactly 60 degrees. This is the measure of the central angle. So this is 60 degrees right here. Once we do that, the third thing we do is we draw the apothem. We normally call A, and find the resulting angle and side length. So we have to know what we're doing with an apothem. Let's go ahead and draw an apothem here between the two radii. One thing is true about an apothem is that it's perpendicular to the opposite side by definition. Another thing it does, we'll come down here now, is this is a radius, this is a radius, this is the apothem. It bisects the central angle that's 60 degrees. It also bisects the side that it runs to. So that's why these tick marks are here and here. So it does quite a few things. So as we take this picture, where this was 60 degrees for a central angle, now we're going to take the central angle measure and we're going to divide it by 2. So that was 60 degrees divided by 2 gives us 30 degrees. So now we have a 30 degree angle right here and a 30 degree angle right here. Next, we also have the length of one side is 3 millimeters. So we take that side and we divide it by 2 because it cuts into 2 equal parts. So this is 3/2 millimeters and this is 3/2 millimeters, or 1.5 or 1.5. So we've got these marked now. Let's come down to just one of the right triangles. This is 30 degrees. This triangle right here. This is A. This length right here is 3/2. Okay, and then the next thing we do, we're going to find the length of the apothem. A, apothem, find the length. So to find this length, notice we have a 30 degree angle, which causes this to be a 30, 60, 90. So we use a 30, 60, 90 Triangle Theorem, which gives us a ratio of 1 to root 3 to 2. Short leg, long leg, hypotenuse. And we've got the short leg, which is 3/2, so we put that under the 1. And then we are looking for the apothem, which is the long leg, so we put a little a under the square root of 3. And we use this as our proportion. So 1 is to 3/2 as root 3 is to a. We cross multiply. 1 times a is a. 3/2 times root 3 is 3/2 root 3, or 3/2 times the square root of 3. We can also rewrite the square root of 3 up in the numerator, so we can write 3 root 3 over 2. So there's our apothem that we need. Our apothem right here. Then we need to find the perimeter. P. So again, the formula for perimeter of a regular polygon is P equal NS, where N is the number of sides, S is the length of a side. So the perimeter in this regular polygon, there are 6 sides, it's a hexagon, times S, which is 3 millimeters. That gives us 18 millimeters. So now we have our perimeter. We have everything we need now, here and here, to substitute in and find the area. So the area is 1/2 times the apothem's length, which is 3 root 3 over 2, or 3 root 3 halves, times the perimeter, which is 18. We can either use this 2 or this 2 to divide out with the 18. I'm going to start with this one. 2 goes into 2 once, 2 goes into 18 9 times. And so that's all we can do. 2 and 3 aren't divisible, 2 and 9 aren't divisible. So the area is 3 root 3 over 2 times 9, which gives us 27 root 3 over 2 square millimeters. Now this is our exact area of this hexagon. The approximation for the area then would be 27 times the square root of 3 divided by 2, about 23.4 square millimeters. So you'll notice in this problem, only been given one side, we have to concentrate on finding the apothem's length. That's the main issue. And the perimeter came pretty quickly because we had a side length. Example 5. Approximate the area of the regular polygon shown below, given the radius is 6 centimeters. Well, so we're going to find the area of a regular polygon, so A equal 1/2 times the apothem times the perimeter. First of all, in this particular problem, we're only given a radius. When this happens, the work can be rather extensive sometimes, depending on the information you're given. N is 9 here, so this is a nonagon. 1, 2, 3, 4, 5, 6, 7, 8, 9. First thing you pretty much always want to do is draw at least a couple of radii, if not maybe 3, to kind of get an idea of what's going on here. So I'm going to draw this radius. I'm going to draw the one over here, and I think I'll draw one more adjacent to that one. You could draw all of them if you wanted or needed to. The next thing you want to do, and this will be helping us define A, the apothem, is that you want to find the central angle measure, just like we did last time. So central angle measure is 360 or 360 degrees divided by N. Here N is 9, so 360 degrees divided by N, and that gives us the central angle measure of 40 degrees. So we can put a 40, let's say right here, that's one of the central angles. This is the central angles, 40, and of course they run all the way through the polygon. This is also 40 degrees here if we pull this triangle out here. Okay, then notice when we use this 40 degrees, if we draw the apothem now, after the radii, draw the apothem straight down from the center between 2 radii. I could have drawn this one too, but we'll just draw one of them. Okay, so now we have a right triangle, and we've taken this central angle, and the apothem cuts it into 2 congruent parts. So we have the central angle 40 degrees, and we divide it by 2 to find our angle in the right triangles, 20 degrees. So now we have, this has been cut. Now this is 20 degrees, so this is 20 degrees right here. This is this triangle here. Okay, so we have a 20 degree angle in a right triangle. Well, we don't have a special right triangle that has 20 degrees as an angle measure. So we are going to have to revert to trigonometry here. We are looking for the apothem's length. This right here or this right here, which remember the apothem is perpendicular to the opposite side and cuts into two equal sides. And then over here, here's one of the triangles. This is 20 degrees. Here's our apothem. This was a radius. These were radii. And so we're looking for the length of a side. Eventually we'll look for that. We're looking for the apothem right now. So the radius they gave us was 6 centimeters. So if this is 6 centimeters, then we've got at least one of the sides, and we've got an angle, and we're looking for this side. So if we're using this angle in reference to this angle, we've got an adjacent side next to it, and we've got the hypotenuse. So that would be cosine. So to find the length of the apothem, we use the cosine of the angle, 20 degrees, and that equals, remember it's cos, C-A-H. Cosine is adjacent over hypotenuse. So adjacent, which is A, over the hypotenuse, which is 6. So this right here is what we start with. Now we go ahead and solve for A by multiplying both sides by 6. And the 6 is divided out here. And A is equal to 6 cosine 20 degrees. Now, don't put that in your calculator. This is the exact value of A. This is what we're going to use in our formula. Before we do that, though, we need to find the perimeter. So the perimeter, we're going to need number of sides times the length of a side. Well, we've got the number of sides, which is 9. So P equal 9 times the length of a side is going to have to be found using trigonometry also. So we come down here and we say, okay, I know this is 6, the hypotenuse. I've got this 20-degree angle, and I'm looking opposite it. So I need opposite over hypotenuse. Well, that would be SOH, S-O-H, sine. Sine is opposite over hypotenuse. So right over here we write sine. This is just to find S here. We're going to use sine of 20 degrees is equal to opposite, which we'll call x, over hypotenuse, which is 6. Now be careful, because when we find x, that's only half the length of a side. This right here is only half the length of a side. The length of the side is double that. So we've got to remember to multiply it by 2. So I'm going to take whatever I find for x, and I'm going to multiply it by 2. So the length of a side is 2x. So when I solve for x here, I multiply both sides by 6. The 6 is divided out, and I get x equals 6 sine 20 degrees. So I take this and substitute it in there. So the length of a side is 2 times 6 sine 20 degrees. And then 2 times 6 is 12. So 12 sine 20 degrees is the length of a side. Now I'm going to use this and put it in here. So S is 12 sine 20 degrees. Now I can find the perimeter by multiplying 9 times 12 sine 20 degrees. So the perimeter is 9 times 12, which is 108 sine 20 degrees. So here's our perimeter. So once again, we have our A, which is right here, and we have our P, which is right here. Now we can substitute that into our formula. A equal 1/2 times A, which is 6 cosine 20 degrees, times P, which is 108 sine 20 degrees. Now, if we're looking for the exact answer, we can get rid of the 1/2 and divide it out either with the 1/8 or the 6, like this. I'll divide it out with the 6. 2 goes into 2 once, 2 goes into 6 3 times, and we're left with 3 cosine 20 degrees times 108 sine 20 degrees. And we can simplify just a little bit more by multiplying the 3 and the 108, because they're numbers, they're coefficients of both cosine and sine. So we have area is exactly equal to 108 times 3, which is 324. And then we simply put cosine 20 degrees and sine 20 degrees back to back. They're multiplied together. Cosine 20 degrees, sine 20 degrees. This is the exact area. This would be in centimeters squared if they asked for it. However, they asked for the approximation. So we take this and we take our calculator. Make sure you're in degree mode. Because we're about to use cosine and sine, make sure you're in degrees. And then put in 324 times cosine of 20 degrees, close parentheses, times sine of 20 degrees, close parentheses, enter. You get 104.1 square centimeters. So the area of this regular nonagon is very close to about 104 square centimeters.